September 19th, 1944. Réchicourt-la-Petite, France. Lieutenant Edwin Leiper peered through the morning fog that blanketed the rolling French countryside. His M18 Hellcat tank destroyer idled quietly behind a slight depression, one of 4 vehicles from Company C, 704th Tank Destroyer Battalion, attached to the 4th Armoured Division. Through the mist, barely 30 feet away, the distinctive muzzle of a German tank emerged like a phantom. It was a Panther, 45 tons of sloped armour, mounting the feared 75mm KGUK 42 gun that could penetrate over 180mm of armour at 1,000 metres. The Panther's glacis plate measured 80mm thick, angled at 55 degrees, creating effective thickness exceeding 140mm. Its turret front was 100mm of cast armour, against the Hellcat's maximum 25mm of protection. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The Panther's gun could punch through from any angle, at any range, with any ammunition type. One hit would be catastrophic, but Leiper had something the Panther crew did not: speed, acceleration, mobility that defied every assumption German tankers had made about American armour. His 19-ton Hellcat could accelerate from 0 to 30 miles per hour in under 10 seconds. It could sprint at 55 miles per hour on roads, 40 miles per hour cross-country. The Panther, despite its powerful 700-horsepower Maybach engine, struggled to exceed 29 miles per hour on pavement, 15 miles per hour off-road. More critically, the Panther's turret traverse was hydraulically powered from the main engine. At low engine RPM, turret rotation maxed out at 6 degrees per second. Even with the engine at full power, maximum traverse reached 36 degrees per second. The M18's turret, by contrast, could traverse 360 degrees in less than 20 seconds, powered by an independent, hydraulic system that didn't depend on engine speed. Leiper deployed his platoon. Within 5 minutes, 5 Panthers of the 113th Panzer Brigade lay burning in the French mud. The Hellcat platoon lost 1 vehicle. The mathematics seemed impossible. 5 45-ton Panthers, each costing approximately 117,000 Reichsmarks and requiring 9,000 man-hours to produce, destroyed by 4 19-ton tank destroyers that cost $55,000 each and required 4,500 man-hours to manufacture. Over the next 3 days of fighting around Réchicourt, Company C and the rest of the 704th Tank Destroyer Battalion would destroy 39 German tanks, losing only 4 M18s destroyed and 3 damaged. When German tankers finally captured intact M18s weeks later, what they discovered in its construction would challenge everything they understood about American industrial philosophy. The story of how a 19-ton tank destroyer consistently defeated 45-ton Panthers and 57-ton Tigers reveals more than tactical doctrine. It exposes a fundamental divide in manufacturing philosophy, one that would reshape not just warfare but the entire post-war industrial world. The genesis of the M18 Hellcat began not in military necessity but in the shock of the Battle of France. In May 1940, German panzer divisions had smashed through French and British lines, achieving in 6 weeks what 4 years of World War I had not accomplished. The speed of German armoured breakthrough operations stunned military observers worldwide. American Army Chief of Staff George Marshall immediately recognized that existing anti-tank doctrine, which relied on static defensive positions with towed anti-tank guns, would prove useless against massed armour attacks. In April 1941, Marshall tasked his subordinates with developing specialized mobile anti-tank units. The concept was revolutionary. Instead of defending everywhere, concentrate anti-tank forces in mobile reserves that could rush forward to meet armored breakthroughs wherever they occurred. Lieutenant Colonel Andrew Bruce, who would later become general and commander of the Tank Destroyer Force, championed this doctrine with evangelical fervor. Bruce's vision was specific and uncompromising. He wanted tracked vehicles faster than tanks, mounting guns more powerful than tank armament, with just enough armor to protect against small arms fire and shell fragments. Nothing more. Heavy armor was not protection, Bruce argued. It was impediment. Speed was protection. Mobility was survival. In December 1941, as the United States entered the war following Pearl Harbor, the Ordnance Corps issued specifications for a fast tank destroyer. The requirement called for a Christie suspension, a Wright Continental R975 engine, and initially a 37mm gun. The 37mm specification changed rapidly as intelligence about German armor thickness accumulated, first to 57mm, then to 75mm, finally to 76mm. The contract went to an unlikely source. Buick Motor Division, a luxury automobile manufacturer in Flint, Michigan, would design America's answer to the Panzer threat. This represented a dramatic shift in military procurement. Previously, military vehicles had been designed by ordnance engineers within the War Department. The decision to contract civilian automobile manufacturers reflected desperate urgency and pragmatic recognition that Detroit's engineering talent exceeded military design bureaus in certain critical areas. The lead designer was Harley Earl, the legendary automotive stylist who had revolutionized car design in the 1930s, with his emphasis on aerodynamics, speed, and visual impact. Earl's team at the Buick Art and Color section approached the tank destroyer problem not as traditional military engineers, but as automotive innovators. They applied principles from racing cars and luxury automobiles to military hardware, streamlined forms to reduce drag, weight reduction through material optimization, performance through power-to-weight ratio rather than absolute power. Earl's staff even designed the Hellcat logo that appeared on the M18's front corners and on crew patches. This attention to visual identity, borrowed from automotive marketing, was unprecedented in military vehicle design. The result would be the fastest tracked armored vehicle of World War II, and arguably the fastest until the development of the M1 Abrams decades later. But speed alone would not defeat Panthers and Tigers. The M18 needed firepower. The 76mm M1A1 gun, the same weapon mounted on late-model Sherman tanks, was selected as the main armament. This high-velocity cannon had been developed specifically to counter improved German armor. Its 52 caliber barrel, measuring 52 times the bore diameter in length, provided the velocity necessary for armor penetration. With standard M62 armor-piercing capped ballistic cap ammunition, the 76mm gun could penetrate 88mm of armor at 1,000 yards. Against Panther side armor of 45mm or Tiger side armor of 80mm, the M18's gun was devastatingly effective. A hit anywhere on the side or rear of a Panther or Tiger meant penetration, crew casualties, and likely ammunition detonation or fuel fire. Against frontal armor, however, the mathematics were brutally different. The Panther's glacis plate measured 80mm at 55 degrees, creating effective thickness that defeated the 76mm gun beyond close range. The Tiger's frontal hull was 100mm of flat armor. While less effectively angled than the Panther, it still provided formidable protection. American ordnance tests, conducted on captured German vehicles at Aberdeen Proving Ground, claimed the 76mm gun could penetrate a Tiger's front armor at ranges up to 2,000 yards. Combat experience would prove these tests flawed. The test vehicles had been subjected to prolonged storage, weakening the armor's metallurgical properties. Fresh German armor, properly heat-treated and maintained, resisted penetration far more effectively. Beyond 300 yards, frontal shots against Panthers or Tigers with standard ammunition proved ineffective. The shells either bounced off the sloped armor or shattered against the face-hardened steel without penetrating. Late in the war, high-velocity armor, piercing ammunition, designated HVAP or T4, became available in limited quantities. This ammunition used tungsten carbide cores and discarding sabots to achieve much higher velocities and penetration. With HVAP, the 76mm gun could theoretically penetrate Panther frontal armor at 1,000 yards, but HVAP remained scarce throughout the war. Most M18 crews had perhaps 5 HVAP rounds if they had any at all. For practical purposes, the M18 could not win in a frontal engagement against heavy German armor. It had to outmaneuver, and here was where Buick's automotive expertise produced revolutionary results. The M18 mounted a Continental R975C4 radial aircraft engine. This 9-cylinder supercharged power plant, originally designed for aircraft applications, generated 400 horsepower at 2400 RPM and 940 pound-feet of torque. The engine was compact, reliable, and produced exceptional power for its weight. The same basic engine powered the much heavier M4 Sherman tank, but the Hellcat weighed only 17.5 tons compared to the Sherman's 30 tons. Raw power alone was not sufficient. Power had to be transmitted to the tracks efficiently. Here, Buick engineers made their most radical decision. Instead of a conventional, manual transmission requiring skilled shifting, they installed a 3-speed Torque-matic automatic transmission, designated 900 tons. This was not a conventional tank transmission. It was an automotive transmission, adapted for armored warfare, built by Detroit Transmission Division of General Motors, using technology derived from passenger car automatic transmissions. The decision was controversial. Automatic transmissions were still relatively new technology in 1943. They were more complex than manual transmissions, with more components that could fail. They consumed more fuel. They generated more heat. But they offered one critical advantage. Any minimally trained driver could operate them effectively. No skill in double clutching, no timing gear shifts to engine speed, no grinding gears during combat maneuvers. The Torque-matic had 3 forward gears with distinct ranges. First gear operated from 0 to 16 miles per hour. Second gear spanned 12 to 34 miles per hour. Third gear covered 30 to 60 miles per hour. The overlapping ranges allowed smooth acceleration without power interruption during shifts. Cruising speeds were optimized at 12 miles per hour in first, 25 miles per hour in second, and 45 miles per hour in third. On paved roads under ideal conditions, the M18 could achieve 55 miles per hour sustained speed. Test runs with specially prepared vehicles and experienced drivers reached 60 miles per hour. Unconfirmed accounts claim that test vehicles fitted with special tracks achieved 74 miles per hour on the banked oval test track at General Motors' Milford Proving Ground. Whether exactly accurate or not, these figures represented performance that exceeded any tracked armored vehicle in operational service. German tanks, by comparison, struggled to exceed 25 miles per hour on paved roads. The Panther's maximum road speed was 29 miles per hour under optimal conditions, with a skilled driver and well-maintained vehicle. In practice, most Panthers operated at 20 to 25 miles per hour on roads. The Tiger managed 23 miles per hour maximum, more typically 18 to 20 miles per hour. Off-road, both German tanks slowed dramatically. Rough terrain reduced Panthers to 12 to 15 miles per hour. Tigers managed 10 to 12 miles per hour across broken ground. The M18 maintained substantially higher speeds across all terrain types. The torsion bar suspension, with 5 independent road wheels per side, absorbed shocks that would have slowed heavier vehicles. The relatively low ground pressure, despite minimal track width, allowed the Hellcat to traverse soft ground that bogged down heavier tanks. In wet conditions, muddy fields, or snow, the M18's mobility advantage over German tanks increased rather than decreased. But speed required sacrifice, and the sacrifice was profound. The M18's armor protection was minimal by deliberate design. The hull sides measured 12.7 millimeters, half an inch. The hull top was 7.9 millimeters, approximately 5/16ths of an inch. The hull bottom was 6 millimeters, a quarter inch. The turret front was 25.4 millimeters, 1 inch exactly, angled at 23 degrees from vertical. The turret sides and rear were 12.7 millimeters, half an inch, also angled at 23 degrees. The rounded gun mantlet added 19 millimeters, 3/4 of an inch, at the thickest point. These measurements represented protection against small arms fire and shell fragments, nothing more. A German 75mm tank gun firing armor-piercing ammunition could penetrate the M18 from any angle at any combat range. A German 88mm gun would pass through the Hellcat's armor like tissue paper. Even heavy machine guns posed risks at close range. During testing of the T-70 prototype, the Army conducted live fire evaluations to determine actual protection levels. At 75 yards, 30 caliber armor-piercing rifle bullets were fired at the turret side. 9 out of 30 rounds penetrated completely. The implications were sobering. Infantry armed with standard-issue rifles could damage or destroy an M18 under the right conditions. Heavy machine guns would shred the thin armor. The open-topped turret, shared with all American tank destroyers, compounded the vulnerability. The turret had no roof. Crew members were exposed to overhead shell bursts, grenades, snipers, and any projectile with a plunging trajectory. Artillery airbursts were particularly deadly. A single shell detonating above an M18 could wound or kill the entire crew with fragments. This vulnerability was accepted, even embraced, by Tank Destroyer Command. General Bruce argued that closed turrets provided false security. Better to have excellent visibility and awareness than dubious protection. Better to see threats early and avoid them through speed than to absorb hits through armor. The open turret gave M18 crews 360-degree visibility. They could observe threats from any direction without rotating the turret. In ambush situations, this awareness often meant the difference between firing first or dying first. The doctrine had a name, repeated endlessly during training: seek, strike, and destroy. Tank Destroyer Battalions were conceived as mobile reserves, held back from the front lines, concentrated under Corps or Army control. When German armor massed for a breakthrough, tank destroyers would rush forward at high speed, racing to blocking positions before the panzers could exploit their penetration. They would engage from concealed positions, using terrain for protection, firing at vulnerable flanks and rears of the advancing German columns. After inflicting maximum damage, they would relocate at high speed before German artillery could range them, or before supporting German tanks could maneuver for counterattack. The doctrine required several conditions to succeed. First, intelligence had to detect German armored concentrations before the attack. Second, roads had to remain open for rapid tank destroyer movement. Third, suitable defensive terrain had to exist at the critical points. Fourth, crews had to exercise perfect fire discipline, not revealing positions until the ideal moment. Fifth, coordination with other units had to function flawlessly to prevent friendly fire and to ensure supporting artillery could suppress German infantry. Reality would prove different. German armor rarely massed for the breakthrough attacks American doctrine anticipated. After the failure of Operation Citadel at Kursk in July 1943, German strategy shifted to mobile defense, using armor as fire brigades to plug breaches in the line rather than massing for offensive operations. The carefully conceived tank destroyer doctrine, based on countering German blitzkrieg tactics, encountered an enemy who no longer employed those tactics. Instead, M18 battalions found themselves parceled out to infantry divisions in company or even platoon strength, providing direct fire support. They blasted pillboxes that resisted infantry assault. They interdicted German movements along roads and trails. They destroyed fortified buildings in urban fighting. They provided mobile artillery for infantry advances. These were not the missions the Hellcat was designed for. The thin armor and open turret made it vulnerable in sustained combat. The specialized anti-tank ammunition loadout was less effective against fortifications than dedicated assault guns with high explosive rounds. Yet the M18 excelled in these improvised roles. The speed allowed rapid repositioning to support infantry advances. The powerful 76mm gun, while optimized for anti-tank work, could still demolish buildings and fortifications. The excellent visibility, and from the open turret, helped crews spot targets and coordinate with infantry. The rapid turret traverse allowed quick engagement of multiple targets in urban environments, where threats appeared from unpredictable directions. Production of the M18 began in July 1943 at the Buick plant in Flint, Michigan. The facility had been rapidly converted from automobile production to war materiel. Buick was already producing B-24 bomber engines, reaching 2,000 engines per month by 1944, far exceeding the initial target of 500. They manufactured cylinder heads at rates of 125,000 per month, 5 times the original specification. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The same industrial efficiency would characterize M18 production. The first contract, designated T6641, called for 1,000 vehicles. A second contract, T9167, added 1,507 more. Production peaked at 250 M18s per month in January 1944. Total production reached 2,507 vehicles by October 1944, when production ended after just 15 months. Unit cost was $55,230 per vehicle, equivalent to approximately $746,000 in current purchasing power. The manufacturing process revealed Buick's automotive expertise applied to military production. The M18 was not hand-built like German tanks. It was mass-produced using assembly line techniques refined over decades in automobile factories. Components were manufactured to precise tolerances using specialized tooling. Dies stamped hull panels from sheet steel in hydraulic presses, ensuring every panel matched exactly. Jigs positioned components during welding, guaranteeing consistent alignment. Quality control used statistical sampling and measurement rather than individual inspector judgment. The result was unprecedented standardization. Any turret built to specification would fit in any hull. Any transmission would bolt into any engine compartment. Any road wheel would mount on any suspension arm. Parts were truly interchangeable, not merely similar. A maintenance unit could strip damaged vehicles for components and install those components in other vehicles without modification, without fitting, without adjustment. This standardization extended to the smallest details. Fasteners used standard thread patterns. Electrical connectors were identical across all vehicles. Hydraulic fittings matched throughout the fleet. Tools to maintain one M18 worked on every M18. Technical manuals applied universally. Training on one vehicle prepared crews for all vehicles. German tank production could not achieve this level of consistency. Steel shortages forced the use of varying alloys with different hardness, requiring different welding techniques and different machining speeds. Component suppliers, often small workshops, lacked precision equipment, producing parts that required hand-fitting during assembly. Quality control relied on master craftsmen inspecting each assembly, identifying problems through experience rather than measurement. The M18's modular design complemented its standardization. Engines mounted on steel rollers integrated into the rear hull. Maintenance crews could unbolt the engine mounts, disconnect drive shafts and controls, then slide the entire engine backward out of the vehicle on the rollers. The engine rested on the lowered rear access door. Mechanics could service or replace the engine without hoisting equipment or specialized tools. An experienced crew could swap engines in under 3 hours. The transmission similarly mounted on rails accessible through a large panel in the front hull. Unbolting the transmission mounts, disconnecting drive shafts, and sliding the assembly out on extension rails required only basic tools. Transmission swaps took 2 to 4 hours depending on crew experience. These maintenance features derived directly from automotive practice, where ease of service determined customer satisfaction and brand loyalty. German tanks required much more complex maintenance procedures. The Panther's engine, while mechanically accessible, required specialized hoisting equipment for removal. The interleaved road wheel system meant damaged inner wheels required removing outer wheels first, a process taking many hours. Transmission work often required partial hull disassembly. In combat conditions, with limited tools and pressed for time, many damaged German tanks were abandoned simply because field repairs exceeded available capabilities. The first M18s arrived in Italy in spring 1944, seeing initial combat at Anzio in May with the 705th Tank Destroyer Battalion. The beachhead fighting provided harsh lessons. The M18's speed proved less valuable in the confined, heavily fortified terrain. The open turret exposed crews to German artillery that dominated the battlefield. The thin armor made M18s vulnerable to any German anti-tank weapon. Crews learned to fight from concealed positions, relocating constantly, never remaining exposed. But Italy also demonstrated the M18's potential. When German forces attempted local counterattacks, the Hellcats engaged rapidly, firing at German armor from ambush positions, then relocating before return fire arrived. The mobility that mattered less in static defensive fighting became critical during fluid engagements. Initial combat reports were cautiously optimistic. The Hellcat's speed impressed crews. Its firepower against medium German tanks proved adequate. But encounters with Panthers and Tigers revealed the limitations of the 76mm gun against heavy frontal armor at anything beyond point-blank range. Then the M18 went to France, following the Normandy invasion. Of the Tank Destroyer Battalions equipped for deployment to France, only 3 received Hellcats before landing in Normandy. The 603rd, 704th, and 705th Battalions, all assigned to Lieutenant General George Patton's Third Army. They came ashore in late July 1944 as Operation Cobra, the breakout from Normandy, began. The 603rd Tank Destroyer Battalion, attached to the 2nd Armoured Division, the 704th attached to the 4th Armoured Division. The 705th operated as Army Reserve, shifting between divisions as needed. All 3 units participated in Third Army's rapid advance across France in August and September 1944. The pursuit fighting suited the M18's capabilities perfectly. High-speed advances to seize key terrain, brief violent engagements with German rearguards, rapid repositioning to support the next infantry push. Then came Réchicourt. The battle occurred as Patton's advance reached the Moselle River near Nancy. The 4th Armoured Division, spearheading Third Army's drive, pushed across the Moselle on September 12, 1944, establishing a bridgehead. German forces counterattacked almost immediately. 5th Panzer Army, reinforced with newly arrived Panther battalions from Germany, attempted to drive American forces back across the river and restore the defensive line. The 113th Panzer Brigade, equipped with brand-new Panther Osweg-G tanks fresh from German factories, received orders to destroy the American bridgehead. The Panthers represented the latest refinement of German tank design. Their 700-horsepower Maybach engines provided excellent power. Their thick, sloped armor defeated almost all American anti-tank weapons from frontal aspect. Their 75mm KOK-42 guns could destroy any American tank at ranges exceeding 1,000 meters. The Panther crews were confident, even arrogant. They expected to sweep aside American armor with ease. Lieutenant Edwin Leiper's platoon from Company C, 704th Tank Destroyer Battalion, occupied defensive positions near Réchicourt-la-Petite on the morning of September 19th. Dense fog reduced visibility to less than 50 feet. The M18s waited in hull-down positions, using slight terrain folds to conceal their hulls, while turrets remained barely visible. Then the fog shifted, and Leiper spotted the unmistakable profile of a Panther turret emerging from the mist. 30 feet separated them, point-blank range for the Panther's 75mm gun. One shot would obliterate the lightly armored M18, but the Panther crew, advancing through fog, had not yet acquired targets. Leiper made the instantaneous decision that defined the engagement. He ordered his platoon to fire immediately, not waiting for the other Panthers he knew must be following. 4 M18s opened fire simultaneously. The lead Panther exploded as a 76mm round penetrated its side turret armor at extreme close range. The second Panther, directly behind the first, never saw the threat. Its turret was traversed to the left, searching for targets. An M18 round penetrated the right side turret, killing the crew instantly. The third Panther attempted to traverse toward the American tank destroyers, but turret rotation at 6 degrees per second meant 12 seconds to rotate 72 degrees. The Hellcat fired 3 times in those 12 seconds. 2 rounds penetrated, 1 through the turret side, 1 through the engine deck. The Panther erupted in flames as fuel ignited. The 4th and 5th Panthers attempted to reverse, backing into the fog to escape. One succeeded, disappearing into the mist. The other backed directly into a stone wall, immobilizing the vehicle. The M18s shifted fire, penetrating the Panther's thinner rear armor repeatedly until the crew bailed out. The engagement lasted perhaps 3 minutes. 5 Panthers engaged, 4 destroyed, 1 disabled and captured. 1 M18 had been hit by return fire from one of the doomed Panthers, penetrating the turret and wounding 2 crew members, but the vehicle remained mobile. Leiper immediately relocated his platoon, moving 500 yards to alternate positions. Standard tank destroyer doctrine: never fire from the same position twice. German artillery and additional Panther companies would converge on the engagement area within minutes. The M18s raced to new positions at 30 miles per hour across muddy fields, arriving and occupying hull-down positions behind a low ridge before German reinforcements appeared. The 113th Panzer Brigade committed additional forces, attempting to overwhelm what they assumed was a small American outpost. Over the next several hours, the patterns repeated. Panthers advanced through or around the fog. M18s engaged from ambush positions, firing at vulnerable flanks and sides at close range, where even standard ammunition penetrated reliably. After each engagement, the Hellcats relocated rapidly, using speed and terrain to break contact before German return fire could be directed effectively. By late afternoon, when the fog finally lifted, 10 more Panthers lay destroyed around Réchicourt-la-Petite. Company C had lost 2 additional M18s, both to supporting German tank destroyers that had accompanied the Panther attacks. But 15 Panthers destroyed in one day represented catastrophic losses for the 113th Panzer Brigade. Each Panther required 9,000 man-hours to produce consumed strategic materials Germany could barely afford, and most critically, carried a trained crew that could not be easily replaced. The battle continued for 3 more days. The 113th Panzer Brigade, reinforced with additional Panther companies, attempted repeated attacks against 4th Armoured Division positions. Each time, M18s from the 704th Tank Destroyer Battalion engaged, using speed to reach threatened sectors, mobility to achieve flanking positions, and firepower to destroy German armour before German guns could traverse to engage. On September 20th, Company A engaged Panther companies attempting to envelope the American southern flank. The Hellcats raced cross-country at 35 miles per hour, arriving at defensive positions before the Panthers could exploit their advance. Engaging from concealed positions at ranges between 200 and 500 yards, Company A destroyed 11 Panthers, while losing 1 M18 to a long-range shot from a German tank destroyer. On September 21st, Company B supported infantry defending the village of Bézingey-la-Petite. Panthers attempted to penetrate into the village from 3 directions simultaneously. The M18s moved between positions at high speed, appearing at critical points just as Panthers emerged into killing zones. By day's end, Company B was credited with 8 Panther kills against 2 M18s lost. On September 22nd, as the German attacks finally subsided, the 704th Tank Destroyer Battalion tallied results. 39 German tanks destroyed, predominantly Panthers, 4 M18s destroyed completely, 3 damaged but repairable. The unit had lost fewer than 20 crew members killed or seriously wounded. The 113th Panzer Brigade, by contrast, had been effectively destroyed as a combat unit, having lost more than half its armour and substantial casualties among irreplaceable trained crews. The kill ratio approached 10-1. More remarkably, every destroyed M18 could be replaced within weeks. American factories continued producing Hellcats at 250 per month. Buick could replace the 7 M18s lost or damaged at Réchicourt in approximately 1 day of production. The 113th Panzer Brigade's 39 Panthers represented roughly 1 month of total German Panther production from all factories combined, and those factories operated under constant Allied air attack that randomly disrupted production schedules. Word of the engagement spread rapidly through American and German forces alike. For American crews, Réchicourt validated tank destroyer doctrine spectacularly. The M18 could defeat Panthers, could defeat Tigers, if employed according to its design philosophy. Frontal engagements remained suicide. but mobility was survival. Speed enabled tactics that negated German advantages in armor and firepower. The lesson reinforced training. Never fight fair, never engage frontally, always use speed to achieve superior tactical position. For German forces, Réchicourt was profoundly disturbing. Panthers were supposed to dominate American armor. A single Panther crew, properly employed, should destroy multiple American tanks before being threatened. The thick frontal armor should provide confidence to advance aggressively. The powerful gun should kill at ranges where American weapons could not effectively return fire. None of these expectations had materialized. Instead, the Americans had used speed and tactical flexibility to negate every German advantage. The M18s appeared from unexpected directions, fired from ambush, relocated before German crews could respond. The lightweight American tank destroyers seemed to multiply, appearing in multiple locations, creating the impression of forces much larger than reality. German commanders could not predict where M18s would appear next, could not pin them down for artillery strikes, could not mass forces to overwhelm them before they scattered. The psychological impact may have exceeded the material losses. German tank crews, accustomed to technical superiority over Allied armor, faced an opponent that regularly defeated superior vehicles through superior tactics, enabled by superior mobility. Confidence eroded. Caution replaced aggression. Panthers that should have advanced boldly instead moved tentatively, wary of ambush, hesitant to expose flanks. The lessons would prove invaluable when German forces captured intact M18s in subsequent battles. The first captures occurred during German counterattacks in October and November 1944. Several M18s were disabled by mechanical breakdowns or combat damage in forward positions that German forces subsequently overran. At least 2 were captured essentially intact, abandoned when their crews were forced to retreat. German ordnance teams transported the captured vehicles to evaluation centers in Germany. The Waffenamt, the German Army Weapons Testing and Procurement Agency, coordinated the examination. Engineers from tank manufacturing firms participated. Representatives from the Army's technical services attended. Everyone wanted to understand how the Americans had built a tank destroyer that consistently defeated heavier, more powerfully armed German tanks. The examination began with the automatic transmission, because nothing like it existed in German armored vehicles. Engineers disassembled the Torquematic completely, documenting every component. The complexity initially surprised them. Automatic transmissions required planetary gear sets, hydraulic clutches, and sophisticated control valving. More components meant more potential failures, yet American forces seemed to report minimal transmission problems. Further investigation revealed why. The Torquematic was overbuilt for its application. Components were designed with generous safety margins. Hydraulic pressures were lower than theoretical optimums, sacrificing some efficiency for reliability. Materials were specified conservatively, using proven alloys rather than exotic alternatives. The design philosophy prioritized dependability over absolute performance. This approach contrasted sharply with German practice. German transmissions used advanced metallurgy and precision machining to achieve maximum performance from minimum weight. Components operated near their stress limits to optimize power transmission efficiency. The designs were elegant, sophisticated, and temperamental. They required skilled operators who understood how to avoid overloading components. They demanded skilled maintenance to preserve precise clearances and adjustments. The M18's transmission required no such skill. The driver selected a range, and the transmission handled all gear selection automatically. Overloading was nearly impossible because the transmission simply slipped rather than braking. Maintenance involved checking fluid levels and changing filters at specified intervals. Any competent mechanic could service the unit without specialized training. The implications disturbed German engineers. German military doctrine emphasized technical excellence through skilled personnel. Tank crews trained for months to master their vehicles. Drivers learned precise shifting patterns for different terrain and tactical situations. Gunners practiced ranging and ballistics until calculations became instinctive. Commanders studied terrain analysis and tactical formations extensively. This investment in training produced elite crews capable of extraordinary performance. American doctrine appeared to assume minimal crew capability. Vehicles were designed so that minimally trained personnel could operate them adequately. The automatic transmission meant drivers needed little skill. The turret power traverse meant gunners didn't need to master manual traverse coordination. The simple fire control system meant commanders could direct fire with basic training. Performance came from engineering rather than expertise. Yet the combat results suggested American doctrine worked. Minimally trained American crews in technically simple vehicles defeated highly trained German crews in technically sophisticated vehicles. The mathematics were undeniable. Either American crew quality exceeded German assumptions, or vehicle design mattered more than crew training, or some combination of both factors favored the American approach. The engine mounting system provided another revelation. German engineers documented how the Continental R-975 rested on steel rollers that formed a track system integrated into the rear hull structure. Loosening 4 large bolts and disconnecting fuel lines, electrical connections, and the drive shaft allowed the entire engine to slide backward on the rollers. It moved out onto the lowered rear access door, where it could be serviced or replaced. An experienced crew could remove and reinstall an engine in 2 to 3 hours using only basic tools. German tank engines required fundamentally different procedures. Panther and Tiger engines were structurally integrated into the hull. Removal required specialized hoisting equipment, extensive disassembly of surrounding components, and skilled mechanics who understood the complex interrelationships between systems. Engine swaps at field maintenance facilities required 1 to 2 days, even with experienced crews and proper equipment. In forward areas, engine replacement was often impossible. This reflected different design priorities. German tanks were engineered for maximum combat performance. Every component was optimized, integrated, and carefully positioned to achieve superior battlefield characteristics. Maintenance was secondary consideration. Vehicles were expected to be serviced by skilled technicians at rear area maintenance facilities. Field repairs were temporary measures until proper service could be performed. American tanks were engineered for maintainability in field conditions. Components were modular, accessible, and designed for replacement rather than repair. Performance was adequate rather than optimal. Service could be performed by minimally trained personnel using basic tools. Vehicles were expected to be maintained by their crews or by field maintenance units with limited equipment and skills. The combat implications were profound. A German tank with engine problems often became combat ineffective until transported to rear area facilities. An American tank with engine problems could be repaired in hours by its crew or by forward maintenance teams. German tanks required specialized parts and skilled mechanics. American tanks used standardized components and simple procedures. The suspension examination revealed similar patterns. The M18's torsion bar suspension used 5 independently mounted road wheels per side. Each torsion bar could be accessed by removing a cover plate and unbolting mounting brackets. Damaged bars slid out and replacement bars slid in. Road wheels bolted directly to suspension arms. Damaged wheels could be unbolted and replaced individually in under an hour. German torsion bar suspensions were more complex. The Panther's interleaved road wheel system, while effective at distributing ground pressure, created maintenance nightmares. The overlapping wheels meant that accessing inner wheels required removing outer wheels first. A damaged inner wheel on the Panther required removing up to 4 outer wheels, unbolting mounting brackets, sliding the entire assembly outward, replacing the damaged wheel, then reassembling everything in reverse order. The process consumed 4 to 8 hours depending on which wheel was damaged and crew experience. Winter conditions made the problem catastrophic. Mud packed between the interleaved wheels. When temperatures dropped below freezing, the mud turned to ice, locking the entire suspension solid. Panthers became immobilized until crews could chip away the ice, a process that could take an entire day with limited tools in freezing conditions. Many Panthers were abandoned on the Eastern Front, simply because frozen suspensions prevented movement and German forces lacked time to free them before retreating. The M18's conventional road wheels eliminated these problems entirely. Mud fell away from the widely spaced wheels. Ice formation was minimal. Each wheel mounted independently, so damage to one wheel didn't affect others. The suspension maintenance advantage alone meant that M18s remained operational under conditions that immobilized Panthers. But the most profound discovery came from examining the M18's construction methods and manufacturing philosophy. German engineers measured panel thickness across multiple captured vehicles. They documented rivet spacing, weld patterns, and component positioning. They examined tolerances on machined parts. They studied how components fit together. What they discovered fundamentally challenged German understanding of military vehicle production. Every M18 examined showed identical construction. Rivet holes aligned precisely between different vehicles, within tolerances of 1/100th of an inch. Structural components from one vehicle would fit into another without modification. Panel forming showed identical characteristics across all examples. Weld patterns matched exactly. Component positions were uniform across the entire sample. This was not craft production where skilled workers fitted components individually to each vehicle. This was systematic mass production using standardized components, manufactured to precise tolerances, enforced through statistical process control. Every part was manufactured to specification. Every specification was designed to ensure interchangeability. Every vehicle was assembled from a common pool of components that fit any vehicle in the production run. German tank production could not achieve this level of consistency with available resources and manufacturing systems. Steel shortages forced the use of varying alloys with different hardness properties, different welding characteristics, different machining requirements. Each batch of steel required adjustments to welding temperatures, different cutting speeds for machining, different heat treatment cycles. Workers adapted techniques to match materials, creating variation in final products. Component suppliers, often small workshops, subcontracting to major manufacturers, lacked precision manufacturing equipment. They produced parts using manual methods, skilled craftsmen working to drawings but adapting dimensions to available materials and tools. Parts from different suppliers varied slightly. Assembly workers fitted these varying parts to each vehicle, adjusting, filing, shimming as necessary to achieve proper fit. Quality control relied on master craftsmen inspecting assemblies, identifying problems through experience and judgment rather than measurement against specifications. Inspectors looked for obvious defects, checked that components moved freely, verified that assemblies functioned, but they did not measure dimensions systematically or compare components statistically across production runs. The result was that no two German tanks were truly identical. Each vehicle had unique characteristics. Parts from one vehicle often required modification before fitting another. Field maintenance units learned to stockpile parts from damaged vehicles because replacement parts from supply depots might not fit without adjustment. Experienced mechanics could look at a damaged component and know which vehicle it came from based on slight variations in manufacture. The M18's construction revealed that American industry had solved the standardization problem completely. Components were manufactured on automated or semi-automated equipment with precision tooling. Hydraulic presses stamped hull panels from dies that replicated dimensions within thousandths of an inch. Automated drilling equipment positioned holes identically on every part. Machining operations used fixtures that held components rigidly, while cutting tools followed predetermined paths. Quality control used statistical sampling and measurement. Inspectors measured dimensions on sample components, recorded results, and calculated variations. When variations exceeded specifications, entire production batches were rejected and processes were adjusted. The system ensured that components manufactured weeks apart in different factories would still be interchangeable, because they all met the same dimensional specifications enforced through measurement rather than judgment. One German engineer wrote in his evaluation report, "This vehicle represents industrial manufacturing philosophy fundamentally different from our own. Every component is designed for replacement rather than repair. Every system assumes the operator has minimal training and limited mechanical knowledge. Every manufacturing technique prioritizes production speed and component interchangeability over perfection of individual execution. Yet the result functions as effectively or more effectively than our carefully crafted machines built by skilled workers to high individual standards. The report continued with observations that would prove prophetic. Most concerning is the strategic implication. If Americans can manufacture tank destroyers with such precision, using automated methods and standardized components, they can produce them at rates we cannot match. If components are truly interchangeable across all vehicles, field maintenance becomes simple enough for minimally trained personnel. Disabled vehicles return to action within hours rather than days or weeks. The mathematics of attrition become impossible to sustain. We cannot win a war of industrial production against an opponent whose manufacturing systems enable both high production rates and high operational availability of produced vehicles. These conclusions reached higher German command levels but arrived far too late to influence strategy or procurement. By late 1944, when the M18 examinations occurred, Germany's industrial capacity was collapsing under Allied strategic bombing. Factories operated sporadically when electricity was available and materials could be delivered. Skilled workers were being conscripted for military service, replaced by forced labor with no training and no motivation. Quality degraded steadily. Production rates fell. Even implementing American manufacturing methods would have required industrial reorganization on a scale impossible to achieve while losing the war. What the examination of captured M18s revealed was not how Germany might counter American tank destroyers, but why German defeat had already become inevitable. The M18 represented not just a weapon but an entire industrial system, a system of design that prioritized manufacturability and maintainability, a system of production that embedded quality in processes rather than relying on individual craftsmen, a system of logistics that assumed standardized components interchangeable across entire vehicle fleets, a system of maintenance that enabled field repair by minimally trained personnel using simple procedures and common tools. Germany had superior individual weapons at various points in the war. The Panther was arguably the best medium tank of World War II in terms of firepower, protection, and mobility. The Tiger, despite mechanical issues, remained the most feared tank on any battlefield where it appeared. German tank guns generally outperformed Allied equivalents in armor penetration. German optics were superior. German crew training was more extensive. Yet Germany lost the armored warfare campaign decisively. Lost it because superior individual weapons mattered less than the ability to produce adequate weapons in overwhelming numbers. Lost it because sophisticated technology requiring skilled operators mattered less than simple technology usable by conscripts with basic training. Lost it because perfect engineering requiring specialized maintenance mattered less than adequate engineering designed for field repair with common tools. The M18 Hellcat embodied these American advantages perfectly. It was not the best tank destroyer by any single technical metric. Its armor was pathetically thin. Its gun was marginal against heavy German armor. Its open turret exposed crews to overhead fire. By German standards of technical excellence, it was primitive, crude, inadequate, yet it achieved the highest kill-to-loss ratio of any American armored vehicle in World War II. It consistently defeated German tanks twice its weight, 5 times its armor thickness, with superior firepower. It did this not through technical superiority, but through systemic superiority. Superior mobility enabled by automotive engineering. Superior production enabled by manufacturing standardization. Superior operational availability enabled by maintenance simplicity. Superior strategic sustainability enabled by interchangeable components and rapid replacement of losses. When German engineers completed their examination of captured M18s and wrote their final reports, they included recommendations. Implement automated manufacturing where possible, standardize components across vehicle types, design for maintainability in field conditions, simplify operations to reduce training requirements, prioritize production rate over individual vehicle perfection, Every recommendation was sound. Every recommendation was impossible to implement in late 1944 Germany. The industrial capacity didn't exist. The materials weren't available. The skilled workers were gone. The time had run out. The examination of the M18 revealed truths too late to matter for the war's outcome, but too important to ignore for understanding why the outcome was inevitable. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.